So in the previous video, we saw the pi model for the MOSFET. So in this video, we'll see how to convert the pi model into a T model and use, so it's basically, there are two different models for MOSFET and they're both equivalent. And each one of them is useful in different situations. So first we're going to convert a pi model into a T model, and then we're going to use a T model in a circuit to see how we can, how T model can help us in analysis. So, okay. So in the previous video, we said, in the saturation, ID is half Kn VGS minus VTN whole squared. And we are always concerned only with saturation for amplifiers. And we said small changes in the current divided by small changes in the input voltage, which will be equal to delta IT divided by delta VGS. We can approximate this by the derivative of the current ID, and which will be equal to Kn VOV. Okay, and then we said ID is, let me call this VGS just to consider the case when the S is actually not ground. So then this will be Kn VOV times VGS, and this will be equal to GM VGS. Okay, so this is the current, and we drew the pi model according to this, and the pi model was where I have my input voltage. I'm keeping this open because we have an infinite input impedance at the gate. This is the gate, and then at the drain, and so I know ID will be equal to GM VGS going in. So this is the source, this is the drain. Okay, so this was the pi model. So okay, so I'm going to make a few transformations here. The first thing I want to do is I want to say, okay, I'm going to say this is GM VGS. I'm going to put another current source, GM VGS here again. Okay, and this is the source, this is the drain. So I hope you all will agree that there is no problem in doing this, right? Because I'm not changed anything. This is the same current still, and this is VGS or VI or whatever. Okay, so this is the VGS voltage. Okay. So now, next thing I'm going to do is I'm going to join this point to this point here. I'm going to say I equal to 0. Okay. So now, as long as I say this current should be 0, then nothing has changed. This still is like an open circuit. Okay. Now another thing is, let's see. So from the gate to source, the voltage is VGS. Okay. And the current in this part is GM VGS. Okay. So that means if I replace this with a resistor like this, 1 over GM, this is GM VGS, this is VGS, and the current is 0, this is source. Okay, so now, like, let's see, so the voltage drop from here to here is VGS, right? And if the resistance is 1 over GM, then I can calculate the current here. I will be equal to VGS divided by 1 over GM, which is equal to GM VGS. So, right? So replacing this current source with this resistance here has changed nothing. So the circuit will still, this model will behave exactly the same way as this model. So as long as it behaves exactly the same way, I don't care, right? So I can use this. All right, and then I'll do one final transformation. This is just for aesthetic reasons, and I'm going to move this up, okay, like this. And I'm going to say this current here is 0. This is the gate. This is the drain. I just moved this point here, and this is the resistance between the gate and the source. Okay, and now this is my new model for the transistor. Okay, it's a T model because it looks. It's a T model because it looks like a T, right? And so whenever you see a MOSFET and you know this MOSFET is in saturation, you can replace this MOSFET with this model. as long as you're concerned only for AC analysis. Okay, so now let's use this model in a circuit and see if we can analyze that circuit. Okay, so page number 4. Now let's draw another circuit here. Let's see. Now I'm going to connect this to the power supply VDD, the drain to the power supply, and then I'm going to put RS at the source and then ground. Okay, and then let's say I have VGS plus VI here, and I'm looking at my output at this point. Right. So now let's draw the small signal model for this circuit. So first, if you want to replace the transistor with a T model, so this will be 1 over GM, and there'll be a current source here. This will be GM VGS, right? Or if this is I can just say this is I, right? That means the current in here is 0. And again, so since VDD is constant voltage, so for as long as AC is concerned, that's 0. And then there is a resistance RS between the source and the ground RS. Okay, and then applying my VI here. Okay, so this VI now is with respect to the ground. Okay, and my output is here. All right, so now let's solve for the relationship between input and output VO. So if you look at this particular part of the circuit, there are two resistors in series. So I can use a voltage divider rule. So I'll say VO will be equal to RS divided by 1 over GM plus RS times VI. Right? So that means VO over VI is equal to RS divided by 1 over GM plus RS. All right. Okay. So that's the relationship between input and output. Again, there are a few things to notice here. So this is the drain, right? So since drain is ground, input VI and this VI is with respect to ground. So that means you can consider as if the input is applied between the gate and the drain, right? And the output is at the source. So you can consider the output is being looked at between the source and the drain, right? So that means the drain is common to both input and output. So this is called the common drain configuration. Okay, all right, so that's one. Or this is also the common drain configuration, that because as long as AC is concerned, drain is ground. Okay, now look at what happens here. If let's say if my RS is very big, right? RS is much big compared to 1 over GM, which is actually usually the case. So this implies VO over VI is approximately equal to 1. Okay, so that means my output is equal to the input. So why would I want to do that? Right, I want to do that because this acts like a buffer. Right, my output is always almost equal to the input, and my input impedance now is infinite. Let's look at what the output impedance is. Let's say if I want to calculate RO here. If I want to calculate RO, what I should do is I should ground all my input sources, apply a voltage here at this point, and look at how much current is going in. Okay, so let's do this. If I ground that, and maybe we don't even have to do that for this particular circuit. So I'm going to ground my input 1 over GM, and this is RS, and this is where I'm looking at. Okay, so if you're looking at this point of the circuit here, so this is ground. This is ground. So if you're looking from here, it appears as if 1 over GM is in parallel with RS, right? So RO is equal to 1 over GM in parallel with RS. Okay, and again, if RS is much bigger than 1 over GM, this will be approximately equal to 1 over GM. Okay, so now you have something with very high input impedance and very small output impedance, and voltage gain almost equal to 1, right? So this particular circuit acts like a voltage buffer. Okay, so that's basically when most of the times when you want to make a buffer, you make that with common drain configuration. Okay, so that's how you that's one use of the T model. And another thing to notice here is when, okay, so the point is, when do you choose pi model versus T model? So a simple rule of thumb is, when something is, if source is grounded, use pi model. If source is not grounded, use T model. That's a simple rule of thumb. Now you can arrive at the same answer no matter what model you use, because it's the same, both models behave the same way. But it's just that for calculation purposes, sometimes T model makes your life easier, right? Especially if something is connected to the source, T model makes your life easier. That's pretty much it, so, right? So what we've looked at in this video is how to convert pi model to T model, right? And we looked at the conversion, and we looked at an application of the T model, which is the common drain configuration. Okay, and so as long as configurations are concerned, so far we've looked at two configurations. One is the common source configuration, which is where the gain is GM times RD, right? And this can be big number. And so the common source configuration is usually used to make amplifiers. And then the common drain configuration, which you use to make buffers. Okay, so we'll stop here.